Hi, let's get started. Thank you very much for being here. I want to talk about CHERI here, and specifically what lowRISC is doing to try to drive CHERI forward. Very exciting technology in our opinion. So in terms of what I want to talk about today, I'll give you a little bit of an overview of lowRISC. Why do we believe in open source silicon, and what's our track record there? Then I'll talk a little bit about memory safety. Why is this still an issue today? Talk about the Sonata development platform, which tries to bring CHERI hardware into the hands of engineers. And then also, I'll talk about the area and code impact that CHERI has. And finally, the final slides are about the CHERI Alliance and kind of calls to action, like what can you do to drive this forward if you're passionate about this as well. So a little bit about lowRISC. We believe in open source. So everybody here, of course, loves RISC-V. That's an open standard. And we do open source implementations using RISC-V. And we really believe that open silicon should be everywhere. We believe that same with software. Open source software really kind of stimulates growth, both for open and closed sourced worlds, for commercial and also for academic applications. And we believe the same can be true for hardware. We have a full stack engineering team, so hardware design and verification, compiler and software. And we're located in Cambridge, United Kingdom, and also in Zurich in Switzerland. And NewAE is a company that's located in Canada and Nova Scotia, and they're quite well known for their chip whisper hardware, which is really trying to make it accessible for people to do side channel analysis on their hardware. So that's actually quite exciting, and it's quite a complementary thing they do. They're very good at kind of PCB design, so we can partner with them on the RTL side and on the software side, alongside the training and the PCB design that they have. Okay, so why should you listen to us? So I'll highlight here OpenTitan. OpenTitan has been our flagship project for years now. We have two different versions. One is a discrete top, which is the chip that you can see here. That's an O-grade chip. But there's also an integrated version for people that want to integrate this into their SoCs. And really excitingly, Google announced that they are using OpenTitan in their Chromebook. So this is a real chip based on real open source hardware that's actually going into a commercial product. So that's super exciting. And so it's also like a nice synergy here, because CHERI is all about memory safety, and OpenTitan is a security root of trust. So lowRISC is obviously passionate about open source hardware, but we're also passionate about secure hardware. There is, by the way, if you want to find any of the links that I have in my presentation, you can go on the schedule. I've uploaded a PDF that has a handout, and you can look at all the links there in case you want to look stuff up. Okay, so let's talk about memory safety. That's why everybody's here. Let's talk about CHERI. So why is memory safety still an issue? So first of all, how big an issue is it, right? So the classic numbers that we always quote in these presentations is that Microsoft did a study based on all of the CVEs that they noticed in 2019. And they decided, like, how many of these would actually have been mitigated if we had CHERI hardware to protect against all these memory safety bugs. And they decided that at least 70%, so 70% would have been deterministically mitigated by CHERI. And that's a lower bound, right? So potentially, if we had designed things with CHERI, it would have been even more. And so you're like, okay, well, how big a deal is that? Well, let's see how much this is costing the world, right? So cybercrime estimating at about $10.5 trillion. Now, when I read numbers like this, it's just like mind-blowing to me. Like $10.5 trillion, that's insane. I think if you kind of rank it in terms of like world economies, I think only the US is bigger than that at the moment. So this is the scale that we're talking about. And even something like a very small bug, a single bug like CrowdStrike, even though that was not a malicious thing, that's not an attack by an attacker, it still was $5.4 billion in damage. So that's one single bug. And all of these things can be solved by CHERI. And then the final point on this slide, why should we care? Well, we've seen an investment by Apple on this enhanced memory tagging extension, and this shows that big companies are willing to invest. They're willing to invest in new hardware. They're willing to invest in new hardware that requires you to recompile all your software, to rewrite significant portions of your operating system. So there's already like a real reason to want to do something like this. And now if we look at CHERI, so there's multiple different ways of solving things. So you can rewrite everything that you have in new languages, but then you have to rewrite billions of lines of legacy code. And CHERI allows you to reuse all of that legacy code, but yes, it does require you to have new hardware. And then on the right here, you have a little diagram about how capabilities work. So instead of having single kind of integer pointers, you now have bounds and permissions. And so with the bounds, you can make sure that you can't just access anything beyond what you had allocated for. So a lot of the problems that you have in initial systems is if you declare an array, there's no way for the hardware to know how large that array was. The compiler knows, but the hardware doesn't. So CHERI provides you a way for the compiler to give the hardware more information about what was intended with this pointer, what was intended for this use. Okay, and so we got involved because people took our core, IBEX, and by people I mean Microsoft. They took IBEX, they added CHERI to it, and they called this Chariot. So this is a specific version of CHERI that makes some decisions on how to do compartmentalization and kind of specializes it for the embedded space. And you can go on the Microsoft GitHub page. There's CHERI IBEX right there. And one thing I will highlight here is some work that they did on temporal safety. So you see that there's a Chariot load filter stage, which essentially stops you from loading capabilities that have been revoked. And how that works is if you're trying to revoke memory or trying to do something similar to like garbage collection, you might want to sweep the memory for stale pointers or stale capabilities in parallel and not having to stop the world completely. So this filter stage allows you to say, okay, these pieces of memory I'm trying to revoke. In the meantime, while I'm revoking that, make sure that you don't load this. So you can still run your processor at the same time as your revocation is running in the background. Okay, Sonata. So Sonata is it's a whole SoC, it's RTL, it's PCB, it's software as well. There's this board right here. If you're interested in looking at one of these in person, come to our booth. But you can also buy them on Mauser. So if you're interested in embedded systems and playing around with CHERI, I do recommend going on Mauser and buying one of these. But the FPGA and the RTL and everything is open source. So if you ever feel like you need to make some changes or want some inspiration about like what an SoC that uses CHERI would look like, you can take inspiration here. And I'll say that we did this as part of a project with the UKRI, so that's UK government funding. And we provided more than 100 boards to leading organizations and universities. And the really exciting thing about CHERI, RTOS, and Sonata is the way that it does compartmentalization. We actually have a very nice demo at our booth on how you use compartmentalization, for example, in an automotive scenario where you might have an infotainment system that's both in charge of accelerating your car and also in charge of your music. And you don't really want those two applications to influence each other. And I mentioned a little bit about spatial and memory, temporal safety. And very importantly for our platform is making things accessible. So we have lots of examples and demos on how to use this platform, and everything is open source and documented in that way. I'll talk a little bit about our latest release for Sonata. So this was a release that's very much focused on performance. So we have certain IP blocks like the pulse width modulator or the general purpose I/O block. And these ones initially would always have a cycle latency when you were reading it, but we've actually removed that cycle of latency, so it's actually 2 times faster to access these. Similar for the SRAM, we had initially, you wouldn't be able to do back-to-back loads or stores, but now we've solved that by allowing to have multiple outstanding reads and writes. And the most exciting work actually here is the stuff that we did on the HyperRAM. So we have a specific HyperRAM controller that can deal with capability tags, but before we were issuing 32-bit, single 32-bit writes and reads to the HyperRAM directly. But now we have read and write buffers to do the read and write coalescing to make sure that you can use the bursts, reads and writes in the HyperRAM. And why this is exciting from a CHERI point of view is all these buffers also take into account the CHERI tags and how to deal with that. So that's some really cool work, and that increased the speed by 3 times on average. Okay, now let's talk a little bit about CHERI, the impact that CHERI has. So in terms of area, I see that my table is a bit bigger. So there's actually another row there about CHERI. So if we look at the overhead for PMP, it's about 42% over the regular IBEX, and for CHERI, this is actually 57%. So it's very similar. If you're designing a chip and you're choosing between physical memory protection or CHERI, the area overhead is very similar. And I'll also say like 50% maybe sounds like a lot, but IBEX is a very small core. And if you look at the pie chart here, IBEX actually only takes up about 1.4% of a chip like OpenTitan. So the logic overhead is quite small, and that's also what I indicated on the right here, that if you add PMP to an SoC like OpenTitan, it's about 0.6% for PMP and 1% for CHERI. So my opinion on that is that to solve memory safety vulnerabilities, this is not a very significant area overhead. I will also mention that we used the free PDK 45 and open RAM standards, so we're really grateful that those technologies are open and for us to use to do these types of analyses. And then in terms of code impact, again, my table has gone off the screen. So the highlight number here is, so for embedded systems, we have lots of different libraries. So in free RTOS, there's actually a lot of existing code already. And you don't really want to have to rewrite this if you're using CHERI. So for this particular example, there's about 147,000 lines of code for these networking libraries, and the CHERI wrapper to be able to reuse all of this without any modifications is about 6,000 lines of code. That's on the next line here. So that's about 4%. So we're talking about for this type of networking code, to be able to reuse essentially all of FreeRTOS's networking stack, you need to change 4%. So that's quite reasonable. And if you look at kind of more application class cores, bigger projects, lots more lines of code, actually the amount of changed code actually goes down, right? So like this is a study, the full desktop environment is a study by Capabilities Limited, where they ported 6 million lines of code, and the change was about 0.026%. And we also see that 100 million lines of code have been ported for the Armorello project. And besides lines of code, there's also an impact on memory bandwidth, because now you have pointers. Instead of being integers, they also have this extra metadata. You're actually increasing some pressure on your memory. And so you can see that for applications that are more memory heavy, you do see more level 2 cache misses, and so you have more pressure on your DRAM. So this is also something that you need to consider when you're adding CHERI to your SoC. Okay, finally, call to action. So there's the CHERI Alliance. We're one of the founding members of CHERI Alliance, lowRISC. It's really founded for technical alignment, promotion, and community. If that's something that sounds interesting to you or your organization, please come join us. There's the CHERI Alliance website. Again, all these links are available on the handout that I've put on the schedule. And then there's also a RISC-V standard, super exciting. It was mentioned in the keynote this morning, also very cool. So there's these RV32Y and RV64Y extensions, and lots of extensions that you can do on top of that base. And please do come and have your say. I feel like a lot of the times in the CHERI community, you talk to the same people that are already convinced about CHERI, but it is good to have outside views on what's happening there. Yeah, so thank you very much. Come to our booth. We have our booth in S3. Also come to the talk about CHERI CVA 6 from Capabilities Limited. And feel free to send me an email on nvdmaas@lowrisc.org. Yeah, thank you very much for your attention.
My name is Thomas from MediaTek. IBEX also has a project called CHERI IoT. Can you talk about the standardization between normal CHERI and then later on the extension to support the CHERI IoT ISA changes?
Yeah, that's a very good question. So at the moment, the CHERI ISA, the one that's currently implemented in CHERI IBEX, was made before they started the standardization process. So at the moment, they have some incompatibilities, but we're working quite hard to make sure that the standard that's currently being ratified is compatible, and that you can essentially create one of those extensions that I was talking about here. Hopefully, you'll be able to. We'll make sure that you can essentially add a ZY. I don't know if we would call it Chariot, but essentially like a Chariot version that you could use. No, Y. So Y is the base. So we're making sure that the base extension is compatible with. Yeah, and then the CHERI ISA will have to have another version to make sure that it's compatible with the base. Yeah. The person to talk to about that actually is Tariq over there. If you want to wave your hand.
Hi, I have a question about the area comparison that you did with CHERI and PMP. So on that slide, I was actually not able to see like the number of entries that were implemented to perform a comparison between PMPs and...
Yeah, so the PMP regions I was comparing here with is 16. So that's, you can have 1, 4, 8, and 1, 4, 8, 16, and 64, I believe. So yeah. This one is the 16 regions. So if you do 64 regions, it would be much bigger than CHERI.
Also, I don't know much about CHERI, but I have a question like, won't it be a better comparison if we like go to a specific application developer requirement? Because like if a application developer just needs like let's say 8 regions, then if we do a comparison between PMP and CHERI implementation and area difference, because then we'll better be able to see like in a specific application how difference is the impact.
Yeah. I think it is useful. I think we put a little bit more information on this in our paper. So there's a paper on arXiv about this, and you can find that link in my handout. So there's a bit more information on that, but yes. So if you did 8 PMP regions, it would be a smaller impact for the PMP side. But the reason why we chose 16 is because that's what we use in OpenTitan or Gray, and that's a concrete chip where we have a concrete use case. So I think 16 made sense in that particular comparison. Ask Tariq. The question was whether there's a timeline for the standardization. I think they're going through the final stages of the review right now. I don't know if Tariq, you want to add anything to that?
Yeah, we're in architecture review right now. We were discussing it with Krista and the others yesterday. So.
Well, thank you very much for all your attention. Please do grab us at the booth as well, and have a nice lunch.